You might have seen already on the web page, there is a video from last year from GLSW. That was the lecture on GLSW. And I, of course, invite you to have a look at the video because GLFW is legacy shader code. So, and there's a ton of GLSW out there. So like 30 years of shader language programming for OpenGL. And of course, the last year's Vulkan. People mostly use GLSL for that. So it makes a lot of sense to really know the basics of GLSL. And I think in the video, I point out to all of the important stuff. Vulkan has its own version of GLSL. It's mostly compatible. There are some small differences. So for instance, this idea of sets, OpenGL doesn't have that. Otherwise, it's more or less the same, but as I said, a couple of very small differences between OpenGL and Vulkan. So keep that in mind. You cannot just 100% use GLSL code that was created for OpenGL and use it in your Vulkan code. But you can have a look at it and have a look at how it actually works and learn from that. Of course, the Microsoft world has its own shader language, HLSL, which is as a language a little bit better, probably, as GLSL. And there was an update, a major update, I think in around 2021 or something, where they introduced things like generics and so templates and other stuff, more modern language stuff. But still, you can see the legacy behind HLSL. And the newest kid in town, and that's, in my opinion, this is the future. Okay, this is where shader language is going to, and that's Slang. And Slang is really a new way of enhancing your shader language. This is the way to go. This is how future shader libraries, big libraries, will be created. And I really, really encourage you to get into Slang. Now, don't waste your time on legacy stuff. That's outdated. Okay. So there is the Slang web page, shaderslang.org. You have all the resources for learning. You have all the language features you can learn there. It's a bit scarce about with the examples, but there's a reason for that, and you have also the GitHub. And the nice thing is that the shader Slang compiler is part of the SDK, of the Vulkan SDK. You don't have to install anything. It's already there. If you install the Vulkan SDK, you have the Slang compiler. That's why all my projects now use only Slang anymore, because in my opinion, it really doesn't make much sense to go back to legacy stuff. So let's have a look at why we use Slang and why Slang is so good and why it's really the future. And what you can see from the past is that we have many different shader languages. So these are languages that you can write your shaders into. You can use them with OpenGL, DirectX, Metal. WebGPU has its own shader language. Who would have thought? So everybody comes with their own shader language. On the other hand, you have also different graphics APIs. We have DirectX 9, 10, 11, 12. We have Vulkan, Metal, OpenGL, WebGPU. And we have compilers that compile stuff only for DirectX. They compile it for Vulkan. You can compile HLSL for DirectX 12. You can compile it for SPIRD that can be used by Vulkan. Probably also for Metal and so on. And of course, when you look at the languages, they are very different. So they use different language statements. But of course, the underlying way that they talk to the graphics card is always the same, but it's a different language. It's like I don't know, Italian and German. You can talk to, it's very different way of using things. And most prominently, you lack a lot of modern language features like generics, interfaces, inheritance, modules. All of this is completely missing usually. HLSL had these upgrades, but otherwise it's really not there. Also, you have to, if you want to feed in your game into all of these different platforms, Windows and Linux and Android and Mac, you have to manage a lot of different languages, writing actually the same idea, the same variations, and you have many different variations, permutations. So NVIDIA came up with a solution for that. It's they call it Slang, and it's a high-level shading language. It's open source. You can find it on GitHub. It's part, as I said, it's already part of Vulkan SDK. And it's here to augment and not replace existing languages like HLSL and GLSL. So this is mainly where we are. And the nice thing is that Slang is like a cross-compiler idea. You write something in Slang, you can compile it to HLSL. You write something in Slang, you can compile it to GLSL. You write something in Slang, you can compile it to SPIR-V or metal shader language. So it's like a Swiss Army knife. It's like either you can build your whole library only with Slang, or you can use it as a multiplicator and like feed all of the other systems with one source code base. And it is, the nice thing is that Slang is not like something completely different. Slang is actually built 100% on HLSL. Okay, GLSL would not be a good idea, but HLSL was a good idea. So Slang is real, HLSL is 95% compatible to Slang. So it's not really new. But they took HLSL and on top of it, like created a lot of new stuff and turns it into a modern language and in the Swiss Army knife. So it enables you to write shader code once and deploy it on multiple APIs. You can deploy whatever you write in Slang on for Vulkan, DirectX, CUDA. You can run it on a CPU. You can create an executable file. No problem. I've done that. So yeah, shader C, Slang C compiler can do that. And think about it for a while that this is not a small feat. This is actually not so easy because shader languages are very much targeted for GPUs. And in order to create something that is so generally applicable, is not so easy, also from the compiler perspective. So why would they use or come up with Slang in the first place? So we have a lot of complexity. Large shader code bases become hard to maintain. Usually we start with small shader code, but that can get into the tens of thousands of lines of code, hundreds of thousands of lines of code easily for large projects. And you really want to have a good way to deal with that. You want to reuse code. Now with Slang we have object-oriented inheritance and interfaces and contracts and overriding and things like that. That wasn't there before that. Portability, so we can write it once and push it everywhere that we like. We can turn it into other languages by cross-compiling or not. We can immediately use it for Vulkan if you turn it into SPIR-V. So we have these modern features, interfaces, generics, abstractions, exporting modules, locality, and of course, what they come up with always is a good way of tooling, and that's something that it really will change the way that you actually see creating programs for GPUs, and we will have a look at reflection in the course of this lecture. Yeah, by the way, before I forget, next week there is no lecture, okay? I will stop here. I will record the rest of the lecture on Slang. I will put it into the web, but next week on 15th there is no lecture, okay? Just I will send out an email also for that. So what are the design goals for Slang? We want to have better productivity. We have inheritance, object orientation. We have abstraction with generics. Portability, write once, target multiple backends. We have, of course, top performance with optimization. Modularity, we can create modules. We can partition our shader libraries. We can have abstraction. And yeah, and we have this rich reflection. And this is something that is a great thing by itself. And also because NVIDIA is NVIDIA and they are very much deep into machine learning, Slang has a big feature that's only about derivatives. Okay, so if you're training your machine learning models, you need derivatives, and Slang has that built in. So that's a big part of the language already. So let's have a look at Slang and how that looks like. On the first glance, it's totally HLSL. So this is what you would expect from HLSL. Most valid HLSL code is also valid Slang code by design. That was a big part because you don't have to throw away your source code. It's already Slang compatible. That's nice. So what's that? So that's just a function. You put in two input parameters. You return here an operation on that. This is the return type. Totally normal, what we would expect from any kind of C, C++, HLSL, GLSL even language. We have the usual scalar types. We have integers, we have unsigned integers, floats and doubles, booleans, half precision floats, which are used on GPUs nowadays. You can set them, give them values like this. Again, totally normal, what we would expect. But then, of course, we have the vector formats and matrix formats that we also expect from a shader language, and that's HLSL. That's 100% HLSL again. We have two-dimensional float vectors, three-dimensional, four-dimensional float vectors. That's the most, but that's also the most that you need for computer graphics usually. So no more than 4 dimensions. Two-dimensional integer vectors, two-dimensional unsigned integer vectors, four-dimensional Boolean vectors. We have matrix types, 2 by 2 float, 3 by 3, 4 by 4. You probably can also use double here. Then you have, but I haven't used it yet, so take it with a grain of salt. You can create float vectors like this. Float 4 is simply a 4-dimensional float vector, and then you put in all the values in here. Again, with the F saying that this is a floating point number. It's 4 bytes. If it's a double, you would not have an F here, just the number. Now, we can also do the Swizzling, which we know from GPU languages. So for instance, if you have a 3-dimensional vector, then we can assign it a 3-dimensional vector. So this is a 3-dimensional vector. Obviously, it comes from some kind of an input struct. There you have a vector, at least 3 dimensions. It could be also 4 dimensions, but you explicitly take the first 3 dimensions of this vector. That is x, y, z. So this is a swizzle. And so we say that, for instance, pose is a 4-dimensional vector, or color is a 4-dimensional vector. But if you say color dot x, y, z, you only take the first 3 components. If you say color dot x, Z, you take the first and third component. So the swizzles will tell you which components you take out of a vector and in which sequence. You could also say ZYX. If we take ZYX, color.cyx would take first this one, then this one, then this one. So it would reverse the ordering of this vector. So that's the very powerful tool, Swizzles, actually. We can multiply matrices on each other and vectors on matrices, but we don't have like an asterisk. We have to call a function. So the multiplication function, give it the matrices, out comes a matrix, and then we can reuse it again in another matrix multiplication. And that's the well-known world or model view projection product that we have here. Like in normal C or C++, I can create structs here with the curly brackets, put in the parts of the struct, but as is custom in many shader languages, I can give it a semantic meaning. And we will come back to this again. This is what you give these inputs. This is something that the user, the programmer, assigns. So for instance, you say that this is my texture coordinate 0, or just texture coordinate. You can give it an index also, or you don't. Then you have just one texture coordinate. And when a stage outputs data into the next stage, all you have to do is to take care that the semantics are the same. The names don't matter, but the semantics are the same. The semantics are what has to fit. When you output data from one stage and you input it into the next stage, they have to agree on the same semantics. Okay. Everything that starts with SV is a system value. This comes from the language itself. This is fed by the GPU. Everything that does not start with SV comes from the programmer. This is the semantic that you give to the variable. We can create functions very easy with a void return or with input or output variables. So here we have to explicitly say this is just an input variable, this is an output variable. So when we write a new value on top of that, result, so if we change result, the calling function will actually see that. So the result will go upwards into the calling function because it's in, out, or in, out. We can have, of course, for loops and if statements. These are standard control flow statements, if, else, switch. Loop for looping, we have for, while, do while, and we have the usual break and continue. Discard means you would discard in the fragment shader, you would discard the pixel or the fragment, and you would not draw it. That's something that you have to do sometimes. Now, for loops are not a problem, but if loops or if statements should be used with care. The wavefronts or warps or subgroups, are they called in Vulkan, usually don't like that too much. When you run a shader code, you run it massively in parallel. Okay, you run the same shader code on many, many fragments or many, many vertices in parallel. And because you don't have that many shader units, what you do is you do a limited it's a single instruction, multiple data. And that's called a wavefront or warp or a subgroup. So if you have a subgroup running, which is like let's say it's 16 vertices that you're working on the same time. Some will fulfill the if statement, some will land in the else branch. Okay, but because it's SIMD, you can only operate one single instruction. And that means that you run into a subgroup where half of them will land in this branch and half of them will land in this branch, you have to do this in sequence. You're not no longer doing stuff in parallel. So first you will do this branch, the other are waiting, then you do this branch, and another vertices are waiting. Okay, so you have a SIMD paradigm in the subgroup of what you're working on. So do this with not too much, I would say. It takes away a little bit of performance. So here we have like light count, and as I said, if you have a specialization constant, you can change that. So the number of loops you can change with the specialization constant. That's not a problem. Yes, so how can we link stages of a pipeline together? We will see an example for that shortly. And we do this with the semantics. So we do this with the semantic that either you or the system assigns to the input and output data. So this would be a structure, and this is one of the naming schemes that is popular. This is the vertex shader output structure. So this is what goes out of your vertex shader. This is an HLSL style semantic. You don't have that in GLSL. You have a little bit different ideas in GLSL. But with HLSL, you assign these semantics with a column. And what goes out will be consumed by the next stage, and they have to have the same semantic meaning. The name is not important, but what is important is the semantic. So let's see that with an example. I hope you can see that. So let's say this is my vertex shader. So this is my vertex shader. Shader vertex. We have a name. By the way, Slang will automatically deduce that this is a vertex shader, simply because we have shader vertex here. And when you load the SPIR-V file, it will automatically choose this as for the vertex stage. Okay, so this is my vertex shader. It's called vertex main. It has input parameters, which are here, and it outputs a struct, which we call vertex stage output. So this goes into the vertex shader, the gray ones, and the yellow one goes out of the vertex shader. So what does the yellow one look like? The yellow one has this as a part. This is simply what is passed from the vertex shader to the next shader. And then we have this SV position part. This is a mandatory thing. Every vertex shader has to output that. And that's simply the normalized device coordinates. That is simply the local position times model view projection matrix of the vertex. You have to output that. And it's very easy. You mark it with SV position, and then it is clear. This is the normalized device coordinate. Whatever the name is, doesn't matter. It has to be a 4-dimensional vector. But because you marked it with SV position, compiler knows and Vulkan knows, yes, this is the normalized device coordinate output of this vertex. But we want to output much more information, so we put it all in this struct. We call it coarse vertex, and we give it a semantic coarse vertex, which has the same name, but it doesn't matter. So we have two semantics that we are outputting, coarse vertex and SV position. So where does this come from? This is the input that flows into the vertex shader. Yes, this comes from the vertex buffer. Okay, so this is at location 0, 1, 2, 3. This is simply coming into the vertex buffer. We bind the vertex buffer. We set all the attributes. And so in goes a position in local space, normal vector in local space, texture coordinates, and a tangent vector in local space. And we give it a semantic, a position, normal, texture coordinates, and a tangent. So this is the semantic that we give it but that's actually not so important. What is important is the semantic of the data that's going out of the shader stage. So so here in the vertex shader, we simply multiply position in the world is local position times world matrix. Position in view space is world position times camera, and so on. Then we fill the output structure, and then we say SV position, normalized device coordinates, is the position in camera space times the projection, the camera projection matrix. So the output is actually local space times model view projection matrix. And then we say return output. So we create the output structure here, which has this type, fill all the stuff and output it. So this goes out. This here goes out of the vertex shader. And we have two semantics on top of that. And inside here we have more semantics. So the next stage has to ingest that. So here we have the fragment shader. It ingests what's coming from the vertex shader. Here the vertex shader again, it's the same vertex shader. We output the vertex stage output. It goes into the fragment shader, and there is no SV position. It's only coarse vertex here. So this is the semantic coarse vertex that we defined here. This goes out and goes into the fragment shader. SV position is not necessary. We don't need it. We can get it, but we don't need it because the rasterizer needed that actually. And in the fragment shader, we are past it. We are already after the rasterizer. So we are not really using the SV positions here. We just use what the rest of the stuff that we output. And that was that here, the coarse vertex stuff. Position in world, normal vector in world, tangent vector in world. And so that's the semantic that we ingest and that we can then make use of. And that's the same semantic. That has to fit. So yeah, that's what Slang does with semantics. So Slang, of course, also offers some object-oriented view. It uses classes. It offers us the way of abstraction. Of course, we can hide implementation details. We can have different BRDF models, for instance, different light models, different physically based rendering models. We can reuse code, of course, with some common logic via inheritance. We can use polymorphism by using interfaces. We will see that later on. So, of course, the whole object orientation will help us structure the code. And that's the big thing here. Slang wants you to have an efficient, well-managed shader language library for your hundreds of thousands of shader language lines of code. So we can create our class, which is the same idea like in C++, for instance. We create a class, give it a name. It has some member variables and it has member functions. Okay, so exactly the same idea as you would have in other languages. And then, of course, I can make an inheritance. So this would be a simple material. It has a base color, it has roughness, and then I say shade. Okay, simple material. What about a physically based rendering, PBR material? That's actually a simple material, but it also has a metallic component to it. And it uses a new member function that's also called shade, but we explicitly override the shade function from the base class. So we inherit members and methods, but we can override the methods by using the override keyword. And for that we can create our hierarchies of materials and lights and so on. So already we are very much deep into object-oriented thinking here. We don't need even to know the structs or the classes. We can build something that's called an interface. And that's like a contract of methods that a class must implement So it's like an abstraction of classes. So we can use, for instance, we can call an highlight, we can call an interface, and we demand that every class that implements this interface must offer also a method that's called illuminate. Okay, so then we render our light on top of the scene. And so that's an abstract interface. There is nothing here yet, it's just a contract. You need this method, but we don't have a definition yet, just of the method. But we can now say that a point light is also implements the interface of light. Yes, it has a position, intensity, and it has a method illuminate. And we can also have a directional light that also implements the interface highlight, but it has different member variables. It has a direction and an intensity, but it also must implement the method illuminate and so on. So now, now for this we can create polymorphism, because the shader code can operate on interface types and doesn't have to deal with the classes or the implementations that are actually used. So here, calculate total lighting. We ingest an array of highlights, whatever that highlight is. It can be a directional light, it can be a point light. It's an array of lights. And you simply loop over this array and then accumulate, for each of the lights, you accumulate the contribution to your to the fragment light, add up stuff, but you don't really know what that light is. You just know it implements the interface highlight. That means that each of these lights must have the illuminate method that you can call. I've shown this already. Shader entry points. Shader entry points define where your shader actually will call in. So if you have a vertex shader, you mark this method with shader vertex, and you can mark this method with a shader fragment. And that means that this is the entry point when you use this SPIR-V file. It's in the same file, it's in the same SPIR-V file. And if you load it, you know that this will be the entry point for the vertex shader, and this will be the entry point for the fragment shader. And then we can have other entry points also, like for pixel shaders, for geometry shaders, for compute shaders, regeneration shaders, and so on. Like C++20, Slang also offers you the possibility to organize and reuse your code with modules. So module is really a collection of classes and structs and methods that are kind of encapsulated and that offer some functionality, but otherwise are opaque. You cannot really look into it, and you shouldn't look into it. So it's a collection of programs that are here to do something very specific. So it's a modern approach to manage shader complexity. As I said, C++20 offers the same thing, and I think it's gradually coming that people are making use of modules also. So you can really organize your big monolithic shaders into self-contained parts. So you break your whole source code into modules that have one specific focus, and the modules export functionality to the outside world, and then the outside world can actually use it. So let's say we have a file lighting.slang, and you define here, this is the module myCoolLighting, and then you can define stuff. You can struct a light, you can a light structure, you can define some methods and so on. So you have your module light, and then you have your main shader.slang, and here you import myCoolLighting, and then you can use it. So this could be your fragment shader, and by importing the module, you can actually make use of it. You might be forced to use export here in order to force stuff to be visible actually in the outside world. Don't forget that. Um, Otherwise, you might get compiler errors here. But that's actually fairly simple. I use it heavily in the new version of the Werner Vulkan engine, and it works like very nicely. But as I said, I was forced to use the export keyword on many places. Otherwise, it just didn't work. So, what about compilation? Slang uses a lot of different ways to get you from A to B. So the Slang compiler parses and analyzes Slang source codes, performs type checking, linking, of course. It generates an internal representation, and then you can translate this internal representation to a target language. So we have many, many different ways of arriving at specific places. So here we start with Slang, and we can immediately compile it into SpearV. Or I can compile it to metal shader language, or I can compile it to GLSL, for instance, cross compiler. I can compile Slang into SpearV and then transcode it into SpearV cross, which then can be transcoded to HLSL, MSL, or GLSL. So this is really a path where you can create all of these other paths. You can compile Slang to DirectX intermediate language, HLSL, metal lib, and then use them directly on your platform. So you see, Slang is really like a Swiss Army knife that allows you to go from one representation to another representation by cross-compiling. And really, there is no dead end here. So you can mix it in your already existing library. And I think this was one of the biggest thing, because otherwise lots of big players would be very reluctant to change to Slang. But now you can simply mix in Slang with anything you already have. And there is no stopping point here. So write once, run everywhere, anywhere, backends. You can use backends for SpearV, HLSL, GLSL, CUDA. You can run it on a CPU if you want. Okay, you can use this for cross compilation. That means that you just have to maintain a single shader code base, which would be Slang, or you can even cross compile GLSL to Slang and vice versa. But you can really have one single code base and cross compile into many other backends. So for instance, if you have a single shader library but you have a project that has been created with GLSL, then you can change your shader code base into GLSL and insert it into this other project. So that's like a Swiss Army knife where you can use Slang with any kind of backend that you want. You can simply mix it in. Now, the main compiler tool, of course, is the Slang compiler, and there is a compiler version for that. So a console version, which is simply a program, and you start the program by calling Slang C. It's part of the Vulkan SDK already, or you can download it from GitHub. So it's this command line tool, and you can simply specify an input file. Usually the extension would be Slang. It's simply a text file. You call Slang C with the text file, and then you can add a couple of options. And there are many options you can choose from. So for instance, you can specify the entry point where you intend that which function should be called when you bind this shader. So this would be the name of a Slang function that should be called when you bind this shader. You can also specify the target. So what should be created? So here in this case, we create SpearV because we are coming from the Vulkan side. but you can also specify many other targets. And depending on the target, then you can specify different profiles, which is simply a collection of settings that you want to ensure. So it could be depending on the type of shader, vertex shader or pixel shader, or coming from Vulkan and being compatible with OpenGL. You could specify something like a GLSL version and then the version that you're targeting. And these are, of course, things that the feature set actually understands. And then you would specify the output that you really want to desire, um, and with -o, and then with the file extension SPV. In this case, it's SPV, and I think the shader, the compiler is intelligent enough that if it simply sees the output file extension, you really don't have to specify, for instance, the target, and it'll figure out that you want SPV as an output. Now it is recommended that you put all your shaders into one file, so vertex shader and fragment shader, and then we will see how you can specify inside your shader file if a specific function is an entry point for a vertex shader or a geometry shader or a fragment shader or other shader types. So at some place, your shader will ingest resources. It will need data to work on. That could be textures that are read in images that are sampled. You can have buffers that contain data, how geometry data, for instance, of your objects that you want to render, or samplers that tell you how to sample like a surface color. And that has to be provided by the application via a graphics API. So we are on the Vulkan side. So we have seen how we can use Vulkan to create buffers and bind them at specific sets and binding numbers. And the APIs are then used to create these buffers and then use specific binding numbers and binding information. And Slang helps you to manage these mappings, and we will see this later on how we can actually do this. So what are the building blocks of shader data? So shaders operate on data, and that can be there can be many different types of data that shaders operate on. So as I said, it can be geometry data, it can be camera data, or rotation data, orientation data, position data, color information. And this data is exposed to the shaders via resource objects. And resource objects have types, so they can have very different interpretations and the way they store data. And the type actually tells now the shader how the data is structured. The data can be structured in a linear way, like an array. It can have different in dimensions that you can access the data. It can be a one-dimensional linear array of data. It can be a two-dimensional texture, color, image that you can sample. It can be even a three-dimensional data that could be like noise in space that you can sample from. And of course, Slang will provide you possibilities to define what type of data you actually look like. There's also a distinction whether it is read only or read and write. So there are different ways to specify that. And there are different operations available. So usually when you have something like a texture, then you can sample it. If it's a buffer, you can load data, or you can use the indexing operator to access it. And you can also load stuff from images, actually. And Slang and HLSL by that matter, because they share most of these data types, will provide specific types, and the type will then have a very specific meaning and will define all of these things. So the type will that you use in Slang will define all of these things. Now, because we are coming from Vulkan, Vulkan is one possible graphics API. It's by no means the only one. And it has its own way of linking resources to a shader. Specifically, we have seen that Vulkan uses descriptor sets and bindings. You can get around that, but basically that's what Vulkan is using. In Vulkan, you also have to specify the layout of the descriptors by using descriptor set layouts. And then you can bind descriptor sets, which are simply collections of resources at specific set numbers. And then in the shader, you can have access to that. So a descriptor set is an instance containing pointers to actual resources. So that could be a buffer, that could be an image view, that could be some structured or unstructured data, sampler states. So that's how you define access, so the type of data that you have at the Vulkan side. Slang will then have the possibility to define where it actually accesses this data and which data it accesses. And for that, we have a couple of attributes or decorators that we can specify. And most notably, we have these three decorators here. There are many others, of course, but we can use these decorators to specify how we access the data. Now, the first one directly maps to our Vulkan data view. And by the way, what you can see here is the namespace. VK is the Vulkan namespace. And you can actually define that you use the Vulkan namespace either by explicitly stating that, or if you create Spear V, for instance, then the compiler will figure out that you're actually using Vulkan, and then it will provide you the Vulkan namespace. So with this attribute here, we can actually specify that a specific resource is situated at a set number and a binding number. So remember, this is what we specify at the Vulkan side when we bind a descriptor set to a command buffer. We bind it at a specific set number, and then inside the descriptor set you have the bindings for the resources. And so if you have a specific resource like this constant buffer, you can now tell it that it will be found by the shader at the set number 0 and the binding number 0 in this example. Now, HLSL has its own syntax. It does not use set number and binding number like this, so it uses these registers, and then you have the specifier on where you can find the resource. Like B would be a buffer, for instance, T a texture, and so on. And then you have different numbers, so you can then have buffer 0, buffer 1, and so on. So this is how you specify it with HLSL, but of course in Vulkan we have this idea of set numbers and binding numbers. So we have to explicitly define it like this. We have other possibilities how to specify where we find resources. With Vulkan, we have this idea of frame buffers and render passes. And inside a render pass, or more specifically a sub pass, we can have access to attachments, color attachments, for instance. And we can use these color attachments to read data from color, or we can write to color attachments. And for both of these options, we can actually use, well, in this would be an input attachment index, so we can read data from a color attachment. Now, when we read vertex information per vertex data, we have seen when we bind a vertex buffer, we can bind several buffers at different binding numbers and then ingest that into the shader. But we have to specify locations for data. And this is the task of this attribute. where we can specify, like for instance, on location 0, you will find the position of the vertex, and at location 1, you will find the texture coordinate of the vertex, and at location 2, you will find the normal vector for the vertex. So per vertex, for every vertex, you can specify the data that is attached to each vertex by providing a location. And you can also use this in the fragment to specify, I think, in which color attachment you write the output. You can write output into several different attachments from the fragment shader. So this would be examples. You have here we have a constant buffer, which is simply a read-only data. And this here, it looks like a generic or a template if you come from the C++ side. And what you specify here is simply the structure of this buffer. And the buffer is actually simply an array of these structs. So this is a struct. It defines the data that you find in the struct, and the buffer is then simply an array of that. We can also have textures that we can read from. This would be a two-dimensional image, and we can specify how we sample from this texture. This would be a sampler state. We will see this later on in more detail. So here we have a couple of more examples. Again, we can specify, for instance, at set 0 binding 0, we have a constant buffer where we have, for instance, per frame data. And at set 0 binding 1, we have per object data when we want that. And here at set 1 binding 0, we have a diffuse map for color information. And here at set 1 binding 1, we have a sampler that enables us to sample from this image. So this would be part of your shader. This is part of Slang. And from the Vulkan side, your task is to create these resources, upload them to the graphics device, and then define the sets, so the set layouts, the scripter set layouts, and then bind them to specific locations. So here we would have the scripter set at set number 0 that contains two constant buffers. And here we would also bind another descriptor set at set number 1. And this set contains an image, a texture, and then a sampler. And from the Vulkan side, we have to create these resources, send them up to the graphics device and bind them. And when we bind it, we can use it in the shader. Now, Vulkan 1.2 and 1.3 will allow you to go a little bit away from fixed indexing, and it will allow you to use something that's called descriptor indexing. So we no more are like bound to a fixed number of bindings, a fixed number of resources, or a predetermined number of resources. So think, for instance, if you have a game that uses thousands of materials or textures, and in each level you use a different number for them and a different and different textures. So using sets and binding numbers explicitly is a big hassle, and from performance-wise is also not the best option if you're really using this many different textures. So what you can do, Vulkan will allow you to, I think from 1.2 up, it will allow you to use descriptor indexing, which is also called bindless. And that's actually where you use a array that can be pre-filled or that can be filled with descriptors for different textures. And so the bindless version in Slang would look like this. So you have an array, but there is no upper number. There is no upper limit for the number of resources that you have in this array. And when you want to use it, you can then specify, okay, which texture I want to use. And then you can, so this is an integer, it's just an index into this array, and then you would simply look into this array, use the bracket operator, and then you have the specific descriptor for the respective image, for the right image that you want to sample. One really very important part of Slang is reflection. So the Slang compiler will compile your shader code and will create some output. In our case, since we are bound to Vulkan, it will be SPIR-V. But when the Slang compiler compiles your shader code, it will have a big size of information about your shader. So which functions are in the shader, which parameters, which data types are in the shader, where does the shader expect this data? It'll try to get access to textures, to buffers, to samplers, and it will look for them at specific set numbers and binding numbers. They will have specific memory layouts because structs are having different fields and different array numbers maybe. And as I said, where they should be bound with descriptor sets, binding numbers. So a lot of parameters about the resources and about the functions and about um, the input parameters that your shader actually expects. Now, your C++ file, the Vulkan side, would probably need to know this also because it has to create all these resources. And usually, when you, in the traditional sense, you would have this complete knowledge on two sides. You have to create the resources on the C++ side. So the C++ side has to know beforehand what type of data your shader actually expects. But because of reflection, a lot of this is actually not necessary because it's enough that the shader, the Slang code knows that. So you can, when you compile it, you can output all of this data and get it to as an input to your C++ file, and your C++ file then can, your Vulkan file can then create the respective descriptor set layouts from that. So your Slang file says, I need at set number 0, I need at binding 0, I need a constant buffer. And at set number 0, binding 1, I need a texture 2D. So all of this information is already there. And this is created dynamically in your C++ file anyway. So it's very easy now to, if you have access to this information, your C++ file, your C++ code doesn't have to know this a priori. It simply loads in the metadata that we get from the compiler and uses that to create all of these descriptor set layouts and binding information. And then with that, you can create your pipeline layouts and then create the pipelines and bind all this information simply by looking at the metadata that it gets from the Slang compiler. And this is the basic idea of reflection. So in Slang reflection, the Slang compiler analyzes your shader code and generates detailed metadata at compile time. Now you can compile Slang files from your console, as we have seen, by calling the Slang compiler, or you can use the Slang API library and link it to your C++ code. So you don't have to touch the Slang compiler at all. The Slang C with your console, you can compile Slang files directly when you start up your program. You can read in the Slang code, or you have it baked into your C++ code, and then call the Slang compiler from your C++ code, because you can do that with Slang. And when you compile it, you can get the metadata directly. So it's a just-in-time compiler, let's put it that way, that creates the SPIR-V output. And when you do that, the compiler library will get you the metadata directly. Now, if you want to use Slang C, you can use the parameter minus reflection JSON and then the name of an output file like here. And what that gets you is simply all the metadata from your shader as a nice JSON file. And then when you start up your C++ code, your executable, you can read in the JSON file and like create all these descriptor set layouts on the fly just by looking into this JSON file. So your C++ application can query the metadata and then understand the shaders requirements and layouts and so on and create this on the fly. And because this is done automatically, you really remove a lot of boilerplate code and you also really remove a lot of error sources because what you do on the C++ side has to like be compatible to your shader needs. And if that's not compatible because you made a mistake or there were changes made and um, you didn't push this to the C++ side, for instance, you have an error situation. It's difficult to find these errors. So better to eliminate the need to synchronize your C++ code with the shader code. Now we have seen that you can use this bindless information, which is the more modern approach in Vulkan actually. And Slang's reflection API can give you the information for that. So which resources are arrays and intended for indexing, and you can then use this in your descriptor set layout binding flags to take care for that. So here these would be information that you get out from the metadata of the Slang compiler, and then you can use that in Vulkan, for instance. So here we have another example how a Slang construct looks like. In Vulkan, we have these things called push constants. That's a very popular way of sending small amounts of memory to the graphics device by binding it to a command buffer. So here with push constants, we don't have to explicitly create a buffer and upload the data and then bind the buffer. We can simply bake this data into a command buffer and then submit it to the queue. However, this makes sense only for a very limited amount of data, like for instance 128 bytes and no more. The limits you can get from the device limits. But on the other side, at the Slang side, there must be a way to ingest push constants. And that's how it looks at the Slang side. So in your shader code, when you expect push constants to be read into the shader, you will use this attribute vk push constant, and then the shader knows, okay, this data comes out of a push constant. So when you submit the command buffer to the device, you will this data you will find coming from the command buffer and not from some kind of set number and binding number. So just by putting this attribute in front of this struct here. And then, of course, you give it a name, and then you can have access to all of this data by simply using the dot and then the name of the of the member in the struct. Now, this is limited to a small amount of data, but when we want to work with larger amounts of data, then we have to use buffers. Buffers represent contiguous blocks of memory. They don't have to be loaded by all of them. There are ways to like bind only parts of that actually. But usually you would actually fill all the buffer with all the data, bind the buffer to a specific set number and binding number, and then in the shader you can use that. So a buffer is actually an array of data, one after the other. It must be created, filled with data, and then the data has to be uploaded to the device. We have seen how we can do that. If it's in host accessible memory or is it in device local memory. Depending on that, you have to construct and fill it differently, maybe using a staging buffer. And there are very different types of buffers. And you can use them for various purposes. So we have seen, for instance, that there are specific buffers for vertex and index data. These are specific buffer types. And you can use buffer by having constants that you use in your shader. You can use it for structured data. So for instance, per frame data, per object data. You can have a buffer that contains raw bytes, like 200, like 8-bit numbers. And then you can have access to the bytes directly. It can be general purpose number, any kind of data that you want to send up. It can be random data number, random numbers that you simply need, noise numbers, noise data, image data. One important distinction is whether the buffer that you're using is read-only or whether it is read-write access. If it is read-write access, then your shader can actually not only read data, but also write data in a very same way that you read the data. And when you write data, then there is also a way of downloading the data from the device to the host again. Now, Slang supports various HLSL style buffer types. I have mentioned that Slang looks very much on a basic level. Slang looks very much like HLSL, and all the buffer types are directly taken from HLSL. So you will find most of them also for HLSL actually. So we will go through the buffer types. We will see how you can create them or define them in Slang. And we will see how you can use them in Slang. And we will start with a constant buffer. We have seen that before. A constant buffer is actually read-only data, typically for uniforms, like per frame data. Could be camera data. Where is my camera? Where is my camera pointed at? Camera parameters, external parameters, internal camera parameters. It can be per object data, specifying where an object is and how it is oriented. So basically, so this is just an input data and it's a structured data. So here we see that it is actually a structure, it is a struct. And inside the struct, we can have typical data types, like here a 4x4 matrix, a three-dimensional vector with camera position, and here some padding. And that's important. So alignment is important, and there are specific alignment rules, and you're really supposed to mind them. If you don't mind them, it will simply not work. And so really, you should learn the alignment rules and really keep that in mind. Now, in HLSL style, we can define a constant buffer like this as a C buffer and then specify where the buffer is bound. I've mentioned this before. B means buffer, and then we have an index number, so we can bind various buffers and buffer types to these binding numbers. In Vulkan, we would probably use something like this here. We have this constant buffer name and then the generic bracket, pointy bracket, and then we specify the struct, the struct type. So here per frame data, and then we give it a name. And here we specify the set number and binding number where the shader expects to find this buffer, or a pointer, a descriptor pointing to this buffer. So once we have that, then we can use all of this information by simply using frame constants and having access to that. Now, this is a structured buffer, but we can also have something like an unstructured buffer, like a texel buffer, for instance, from the Vulkan side. And a texel buffer doesn't have a structure. So for instance, could be a uniform texel buffer here, or from the Vulkan side, it could also be a storage buffer. If it is for read-write. Unstructured means there is no struct, so you will find one specific data type as a big array. So for instance, it could be floating numbers, floating point numbers, or here a four-dimensional vector of floats. So this is a basic data type, and you will find this like an array of these data types. So here we would specify that again. We specify the binding. We specify what buffer that is. So in this case, it would be a read-write buffer, unstructured buffer. We specify what we expect in the buffer. It's an array of unsigned integers, and then this would be, I think, 4 bytes. And then you give it a name. And when you want to access it, you simply use the indexing operator and an index into the buffer, and then you can read or write from this location from the buffer. Now, we have seen constant buffers, but we can also define something where we want to not only read from, but also read and write to, and we can call this a structured buffer. And in a constant buffer, we really weren't able to use indexing, but in a structured buffer, we can. So a structured buffer is an array of user-defined structs. From the Balkan side, we would call this a storage buffer. Yeah, so RV structured buffer is also a storage buffer. This is often used in compute shaders, and this is how it looks in your Slang code. Again, the binding information, and then you have a structured buffer. By using this structure here, and what you can do then is use the bracket operator to index into this buffer. So for instance, in your compute shader, you have an ID of a currently data that you're working on, which is maybe multidimensional, and then you can index into this buffer and read and write from this location or write to this location. Yeah, we can also have raw data without any interpretation. This would simply be very simple data that you can have access to, like on a byte level. And you do this by specifying some kind of an index, and then you index into the raw data buffer and load a specific data from there. So this is really a byte type of access, and this is how you want to interpret this data. So you have raw bytes, and at this specific location, you expect to find a float, which is 4 bytes with a specific semantic. But of course, there is no guarantee that these 4 bytes are really a float. You have to be sure about that. Likewise, you can also, with a read-write byte address buffer, you can store data at a specific location. So this is, but again, the programmer is responsible for keeping the right semantic for the buffer type or for the buffer addresses. Now, so far we have seen normal data that you would expect in many different programs. But now we're coming to images, because images are very important for computer graphics. And we have many different ways of using images in Slang or in computer shaders or in rendering shaders in general. Generally, we talk about textures that we use in order to get color information or normal vector information, or like any other kind of information, and we can sample that. So when we're talking about textures, we usually say mean the texture itself, and then a way to sample it, to get information out of the texture. And in Slang, usually we can simply call sample. So here we would have a 2D texture, which we can sample. And in order to do that, we call the function sample. We have 2 dimensions where we want to do that. And then we also have to use a sampler. And the sampler will not only use this very specific location, but there might be other information attached to the sample, like interpolation or using mipmap levels and how to interpolate between the mipmap levels and so on. So a sampler is simply a way of telling the um, how, the shader how to sample from a texture. We have seen that when we went through the Vulkan API. Now we can have many different versions of textures. We can have one-dimensional textures, which is simply a linear array. We can have two-dimensional textures, which is a simple image. We can even have three-dimensional textures, which is then a way of really having three-dimensional data. Could be like X-ray data, for instance. We can also interpret as six sides of a cube. That is that is a very nice way to have like light probes and shadow maps and things like that. But we can also have arrays of textures. So we can have many textures. And these arrays will allow you to have many one-dimensional or two-dimensional textures that you can actually index into. We can also do this for texture cubes, and we will see this later on how that is actually then organized. We can have read-only textures, and we can have also read-write textures where we can also write into that. So again here, typically in a compute shader, we can simply use the typical indexing operator to write data at this specific location into an image. Now, I said that a sampler tells us how to get data out of a texture. So we have different filtering options, addressing modes, how we use mipmaps and so on. In modern APIs, a sampler is not necessarily part of an image. In Vulkan, you can have that. I can have a combination of sampler and image, but I don't have to. So if I have a sampler as a discrete object, I would call it a sampler state object. And I can use this, for instance, to sample from a normal color image. Now, there are also other types of samplers that I can use. They can use something like a comparing to a specific number. And you use this usually for shadow maps, for instance. We will see this later on how shadow maps work. So when you have a shadow map, for instance, um, then we can sample it and compare it to a specific shadow map by calling sample, compare level 0. And then we get something like a shadow factor, like how much is this fragment in shadow? Is there light coming on this fragment, or is it in shadow, or is it partially in shadow? So usually we can simply program that by sampling and then making a comparison, but Slang will give us the whole operation in one go, so we can use that. And then we can simply sample the color map and then compare this later with the shadow factor, because the shadow factor will tell us if there is light coming onto this color or not. So setting the sampler in Slang directly. So we've seen the sampler state that has to come from somewhere. So here we have created it from the Vulkan side or from the graphics API side and have bound it to a specific binding number and set number. So everything is defined at the C++ side, but you don't have to. You can actually define all of this in the Slang shader itself. So here we have this possibility. We create a sampler state and set all the specific information that we want to use right here in the shader. And then we give it a name, linear repeat sampler. And so this is our mipmap filter. This is our address mode, how we repeat outside of address 0, 1. And then we can use it directly to sample from a um, from a from a from a texture. So here my texture sample, use this sampler, sample at this location, and then we get the result from this texture. So let's have a look at more specifically to these buffer types or these texture types. So we will start with the most simple case. It's a one-dimensional texture, and we give it a specific type of what we're actually expecting. So this could be also, of course, a raw buffer type or something that is simply something like data that we ingest, and this could be also the output of a function, a one-dimensional function that we sample from. Again, we can use a sampler to sample from, or we can load the data directly by calling load and give it an index, and then we can get out the data without sampling. So this is the um, pure data. We can also have a two and one-dimensional texture as a read-write resource. Then we would specify it as a read-write texture 1D, give it a name, specify the data type that we will find in this texture, and then again we can read from that and also write data into that. Again, using the indexing operator, we can specify a specific function that we want to call on the specific location, and then write it back into the texture. Now, the texture 2D is actually the workhorse of computer graphics. So this is really used a lot. Usually it's used for color information and other information like geometry information, normal vector information. You can use it for sampling physically based rendering, material information, metalness, for instance, roughness. You can use it for providing more geometric information like tangent vectors. But all of these information is fundamentally two-dimensional. And so when we're talking about two-dimensional textures, we can use this texture 2D texture type. So this is a two-dimensional grid of texels or texture elements. We can access them at two-dimensional coordinates. So we need two-dimensional coordinates, UV coordinates to specify a specific location in the image. We can use sampling, or we can directly fetch data at a specific location by calling load. And we can use it for color maps, normal maps, roughness, and then so on. In Vulkan, we would use it as a descriptor type sampled image. And in Slang, we would have texture 2D, and then the format of the image. So this is not necessarily always 4 bytes. But in this case, it is actually 4 floating point numbers. So it's a very specific format where every pixel or every texel has a 4 times 4 bytes. So the pixel information is organized like this. And then we also have our sampler, and then we can call texture sample, give it the sampler, give it the location where we want to sample, and we get the information, the sampled and filtered information out from the two-dimensional texture. Again, we can also call load and directly specify where we want to sample, and also the MIP level. We have seen previously in a previous lecture that we can have MIP levels for textures. These are different versions of the texture with different resolutions. Now we can also specify a read-write version of a texture. It would be specified as a Vulkan storage image. And we can sample from that, but also we can write back data. For instance, in a compute shader, we can blur an image, for instance, or have any kind of other post-processing effect We can use edge detection. We can use motion blur, and then like write it back. Now we can also have three-dimensional textures. This would be not only two-dimensional image-like texture, but it would be volumetric texture, volumetric data. And that represents a three-dimensional grid of texels. So that could be, for instance, volumetric data coming out of from an MRI, a tomograph, or it could be noise data, or it could be three-dimensional density data, fog data, flow data. And so anything that describes fundamentally a piece of volume instead just a piece of two-dimensional surface. In order to access that, obviously we need three dimensions for the coordinates. To sample that, we can filter it and sample it by using sampling, or we can load data directly. And from the Slang side, we would again specify it as a texture 3D in this case. And it would be internally, it would be an image that has a view type of a 3D image. Again, we can sample it by using a sampler, and we have to specify a three-dimensional coordinate in order to find the right position where to sample it, or we simply load it. And here we also have to specify the mid level because the sampler actually takes care of the levels, so it will take care of that. But if we don't have a sampler, then we have to specify the mid level ourselves. And then there is the read-write version of that. It's exactly the same idea. We could have three-dimensional floating point vectors, and we can sample that. Now, for cube-like data structures, we can have this kind of texture cube. And that's a specialized texture that represents 6 2D faces. Internally, these are image layers. So because an image can have not only mipmaps levels, but also layers. And internally, a texture cube must have 6 layers. Then you can use it as a texture cube. Now, de facto, this is just an image with 6 layers, and you could access that easily by using just an image with 6 layers. You don't have to use a texture cube. But the nice thing about the texture cube is that you sample it not by normally using coordinates, but you use a view direction vector. So if you look at a cube, then the way to sample it is to assume the midpoint of the cube, and from there goes away a vector that points to a specific side of the cube, and where this direction vector hits one of the sides, there is the place you want to sample. So it's simply a different way of sampling, and for sampling you do not use what you would normally call coordinates. You actually use a view direction. And you would, of course, do this by putting this into the sampler. And the sampler will then translate the view direction to the face index and the XY coordinate on this specific layer and a specific MIP level. If you don't want that, if you want to specify all of this information yourself, again, you can use the load function, and then you have to specify all of this information. You have to specify which of the layers are we talking about of this cube, where on this layer do we want to sample, and which MIP level. Another way of looking at two-dimensional textures is by putting them into an array. So we have seen that texture images can have layers, different layers. And if you want to have access to separate layers, you would simply use texture to the array. And from the Vulkan side, you fill in an image with many layers. And then you can, on the Slang side, then you can have an array type where you have to specify which layer do you want to sample from in the sampler, and give it also the UV coordinate where you want to sample it, and then you get the image information on that specific position on this specific layer. Again, if you don't, if you want to specify this all yourself, you can use the load function. Then you can have to specify also the MIP level for that. We can also have texture cube arrays. Now, a texture cube is 6 sides of a cube, and an array of that means you have an array of 6 sides, and that means that the texture cube array must have a multiple of 6 layers. And on the Vulkan side, you have to specify that the view type is actually a texture cube, and you have to make sure that the number of layers is really a multiple of 6. And then by specifying texture cube array, this could be used, for instance, for shadow maps. If you have a point light, then the point light will shine light in all directions, and you want to capture that with shadow maps. So you have to like have a cube that is centered around the point light, and there's a shadow map in each direction. So you need a texture cube of shadow maps all around the point light. But you can have many point lights. You can have a large number of point lights. And for each of the point lights, you need a texture cube. So using a texture cube array gives you the opportunity to store many, many shadow maps for point lights in one go. And again, because we're talking about shadow maps, we would use not the normal sampler, but like the sample compare level 0, and compare it to the distance of a fragment to the light source, and then we can use the shadow map algorithm to detect whether it's in light or it's in shadow. Now, Slang is meant to be used with different graphics API versions like Vulkan and DirectX and so on. So and they all have their own definitions for bindings and how resources are bound to the shader. And one way to abstract this away in some sense is to use what's called a parameter block. A parameter block is a Slang feature for grouping together related shader parameters. And you can group all of those objects that we have seen so far, like uniforms, textures, samplers, buffers, structured buffers, read-write textures, and so on, into one or several parameter blocks. And using that enables Slang now to figure out some of the binding information by itself, so you don't have to necessarily provide it all the time. So a single parameter block can hold any combination of resource types needed by a shader. And the idea here is to write shader code once and then use it in several graphics APIs. Of course, we can then use also the Slang compile time reflection to find out the structure of parameter blocks. With respect to Vulkan, this would be binding numbers. But for Vulkan, we still would have to specify, as far as I know, we still have to specify set numbers. And if you want to start with a binding number other than 0, you would also have to specify this binding number. Here we have an example. We would have a struct containing material data, like a base color, albedo, a texture, and a sampler. And now we can take this struct and put it into a parameter block. We call it global material. We still have to specify the set number. In this case, it would be set number 0, which would be the default set number. And then we can use this parameter block in our pixel shader, for instance, by simply saying global material and then get access to the interior of the struct. Now, on the C++ side, as I said, we have to create all the resources and we can use Slang reflection to get information about what the shader actually wants, what the shader expects, and we can use the meta information that we get out of the reflection to understand about the structure of this struct, of the global material struct. And once we have understood that, we can create all the GPU resources for that, a constant buffer, a texture and a sampler, the texture and sampler views that we need, and we can get this from the metadata from the reflection out of the compiling of what we need. And then, of course, because we're talking about textures and so on, we have to create that and upload that and bind the resources then accordingly to the descriptor sets and create the samplers, and then we can use that in the shader. Now, on the graphics API side, in our case it's Vulkan, but of course there are many other graphics APIs. We can use the Slang or HLSL types and map them directly to Vulkan. We have read-only resources, which are textures, buffers, structured buffers, and they often map to specific descriptor types like a sampled image, a uniform textile buffer, storage buffers, or uniform buffers. And we use them in descriptor set layouts and descriptor sets to point to the shader resources. And then we have the read-write counterparts. These are the read-write textures, buffers, and structured buffers from Slang, and they often map to storage images, storage buffers, or storage textile buffers. So this is what you would see at the Vulkan side, that you put into the respective descriptor type and then bind that to a command buffer. Let's have a couple of examples for shaders, so you can see how shaders actually look like. Here we would have as an example a basic vertex shader, and the basic vertex shader needs information. The basic a vertex shader is called for each vertex out of a vertex buffer. The vertex shader is called once, so you have a vertex buffer, and in the vertex buffer you have specific per vertex information. That could be, for instance, a position of the vertex in local space, two-dimensional texture coordinates when you want to sample a texture for the surface color information, and a normal vector, for instance, for light information, so you can derive light information later on. And because we get it from the vertex buffer, we use as an attribute the location information. This is what we use when we create a vertex buffer. When we create a vertex buffer, the vertex buffer has, at specific locations, it has this information. And then when we bind the vertex buffer and submit the command buffer, then all of this information flows into our shader. Now we call this vertex shader input. So this gets into our shader. Also, we get something, for instance, worldview projection matrix. We get this out of a constant buffer that we have created before, and we bind it at set number 0, binding number 0. And so this is our geometry information about the objects and about camera, for instance. Camera information also could be in there. Now, this is input data that flows into the shader, but out of the shader comes an output data. So we need another structure, we call it vertex shader output. That is data that is produced by the vertex shader. So for instance, what comes out of it is the positions in normalized device coordinates. And I have already said that we not only specify a name in the struct, but also semantic information. So what's that? Everything that starts with an SV is a system value that is created by the shader itself, so by the shader library, and everything else is a semantic that the programmer attaches to each of these struct members. These are normal, these are like predefined semantics, texture coordinates, normals, and positions. You can use them directly or attach an index here, a number. So you can have more than one texture coordinate or more than one normal information if you want. But this flows out of the shader. So here we would have the vertex shader. We have a decorator with shader vertex. So we know that this is a shader that is used at the vertex stage. We give it a name, we give it the input information here, and we define the output information that is produced by the shader. And in order to do that, the first thing we do is we define um, storage memory to store the output information. And then the last operation is return this output information. So, and this is this information that comes out of the vertex shader with these semantics. Now, this information flows out of the vertex shader, gets into the next shader stage, and has to be ingested by the next shader stage. It is important to understand that the next shader stage will have to define exactly the same structure, but it does not have to use the same names. So the names are arbitrary. They don't have to match. What has to match is the semantic information, because of course all these stage shaders, they can be programmed by different sources. So different sources can have different naming conventions, but what they cannot change is the semantic information. So this has to match the outgoing, the semantic of the outgoing data has to be the same as the semantic of the data flowing into the next stage. What we can do is then we fill up the output information, clip position, texture coordinate, world normal. We do this by using the input information per vertex. So this is the per vertex local position. We multiply it with the view, world view projection matrix, and outcomes in normalized device coordinates, the clip position, or in clip coordinates actually. And the other thing this is just something we pass on. We copy it from the input data and copy it directly to the output data. And then, of course, we also like pass on the normal information, but in this sense, we just multiply it with the normal, with the world matrix, and we get the normal information in world coordinates. Now, this information flows into the next stage. In this case, it would be the fragment shader. So we have the same information with the same semantics, uh, um, system value position. In this case, when it flows into the fragment shader, it is actually denotes screen space information coordinates, because the fragment shader is really not really concerned with normalized device coordinates or clip space coordinates. So in this case, when it flows into the fragment shader, it is already transformed into screen space. And in the fragment shader, we use a couple of resources that are bound to specific positions. So here at the set numbers 1 and 0 and binding numbers, we have a texture to sample, a sampler, and then a constant buffer. In this case, it is light information. So positions of light, for instance, that we can use. So here that would be our fragment shader. We give it a name. We give it the input data that flows into that, but outcomes always the same. Outcomes a four-dimensional information about the color. And that must be a four-dimensional result information. And we can also specify the type, the semantic of the result of the fragment shader, which is system value target. And inside we have the usual computation of sampling the surface color and then using light information. We use the dot product with the normal vector and the light, and then we have some kind of light information, and then we can use that, multiply it on the sampled albino color, and we have the final output, a lit fragment on the surface of this object, and we get the final color output of that. Now, if we have a graphics pipeline, we have various stages where data flows. We have seen the vertex shader outputting data going into the fragment shader. But of course, in between, we have other stages that we can have run our shader code also. So for instance, we can run a geometry shader here. So in between the vertex shader and the fragment shader, we can put a geometry shader. Slang, of course, helps us to manage all of this code. We have seen by using this the decorator for the shader code function, we can specify where this function actually should run. So here we have an example for a geometry shader, and the geometry shader ingests not a single vertex. It can ingest actually a single vertex, but usually it ingests a geometry object. And a geometry object can be a single vertex. It can also be a line or line segment, or it can be a triangle that is ingested by this geometry shader. So in our case, it ingests 3 vertices. It ingests a triangle. Here we have each triangle gets this geometry shader input information, the clip position, texture coordinate, and the normal coordinate. So this is what came out of the vertex shader. And here we feed this into the geometry shader. So we get 3 vertices because each triangle needs 3 vertices. So the geometry shader swallows up a triangle with 3 vertices, each vertex having this information. And then it can emit a number of vertices, and we have to specify the maximum number of vertices that can be produced by the geometry shader beforehand. So this is fixed. We have to specify a maximum number, but this can be set by us, so we could easily specify many more. We don't have to use it. We just have to set that this is the maximum amount of vertices that can be emitted by the geometry shader. So the geometry shader will also create an output, and the output is a stream of triangles, and we call this a triangle stream, and each one has vertex v as output. So this is the same information that comes out of the vertex shader. We simply pass it on to the next stage, which would be the fragment shader actually. So we produce this output stream, and then we design that this is what we want to output. So this is a stream of triangles, and here we would actually create 3 vertices that are produced by this geometry shader, which form up another triangle.